So over here, we've got an expansion, an identity they're giving us, and they want us to prove this expression here. So as you might be able to recognize, this is basically a binomial identity. We've been talking about them in terms of like type 1s and type 2s. And if you do a quick examination here, you'll notice that there's a lot of combinations on one side. On the other side, there doesn't appear to be any combinations, although they've got factorial, so it could be. And so you'll need to then decide, should you be trying to compare coefficients, or should you be trying to sub in a particular value of x? Now, they've given you this particular one. And then you also might want to just pay attention to the fact that they've got fractions. So those are some things that you might want to sort of consider when you're looking at what you might be doing here. Okay, so let's take a look. We've got x squared times 1 plus x to the power of n. Now, clearly, we need to consider 1 plus x to the power of n, which you should be familiar is the sum from k equals 0 to n of nck x to the k. So this would become x squared times the sum of k equals 0 to n of nck x to the k. But, I mean, you're really just multiplying everything by x squared. So that means that basically the powers just go up by 2, right? I can move it in. Or in other words, it's the sum from k equals 0 to n of nck x to the k plus 2. You're basically just taking the same thing, but just making all the powers of x's go up by 2. So your constant term is now an x squared. Your x to the power of n term is now x to the power of n plus 2. So we now have this. And we now want to compare, we want to somehow get, ideally, 1/3 NC0 plus 1/4 NC1 plus 1/5 NC2 plus ... plus -1 to the n plus 3 over n plus 3 NCN. Now, and equals something on the right-hand side that I will ignore for now. So if you compare, you can probably see that, well, the NC0 is going to be x to the power of 2, yes? The NC1 is going to be x to the power of 3, and so on. So if it helps, we can write this out in a sort of more expanded form. So our expression here is saying that we've got NC0 x squared plus NC1 x cubed plus NC2 x to the power of 4 plus blah, 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 plus, well, NCN x to the n plus 2. And then if you compare these two, what might be very interesting to note, of course, is that our x disappears. So you might think about what we want to do to make that happen. But on top of that, as we pointed out earlier, you've got a third, a fourth, a fifth, and an n over n plus 1, 1 over n plus 1, which might be telling. In other words, we're not ready to do the next step yet. We need to still modify this to our sort of purpose. And the way we would modify this identity to make it so that we get this fraction of 1 over something at the front is we would integrate. So we're not done with this. We need to integrate. So we need to integrate both sides. We would say that the integral of the sum from k equals 0 to n of nck x to the k plus 2 dx. Well, this, after all, was equal to this, must equal the integral of x squared times 1 plus x to the power of n dx. Now, this part's easy to integrate and will give us what we want. This, on the other hand, is rather annoying to integrate directly. So it's probably a bit more typically difficult question. We will need to do a little bit of work, okay? So the right-hand side is not too hard, but you probably to be able to make it more doable, you probably let u equals x plus 1. That means du must equal dx, and x must equal u minus 1. In other words, I'm saying this will become u minus 1 all squared times u to the power of n du. And you can see how it becomes more manageable because you're going to have to expand this. And to the power of n is not really all that feasible, or certainly not that easy anyway. So certainly, I mean, we could do it, but then we'll get the same thing. And the whole point is we don't want the same thing, right? So this will become u squared minus 2u plus 1 times u to the power of n du, which is going to be u to the power of n plus 2 minus 2u to the n plus 1 minus or plus u to the n. And that we can definitely integrate. Let's just finish that off on this page first. So we're going to get 1 over n plus 3 u to the n plus 3 minus 2 over n plus 2 u to the n plus 2 plus 1 over n plus 1 u to the n plus 1. And in other words, it's going to equal, we can put the plus c on this side. We're going to need to put the plus c on one side, right? So it's going to be 1 over n plus 1, n plus 3, x plus 1 to the n plus 3, minus 2 over n plus 2, x plus 1 to the n plus 2, plus 1 over n plus 1, x plus 1 to the n plus 1, plus c. So that's the right-hand side. The left-hand side might be a tad easier at this point because you just integrate x to the power of x plus 2, which of course is 1 over x plus 3, x to the power of nck, x to the power of nk plus 3. And you're still going to have the sum from k equals 0 to n, of course, of this thing. And that's the left-hand side done. Okay, so it's actually pretty easy, the left-hand side. Now, our job after integration, of course, is to find the c, which I have currently put on the right-hand side. I'm going to put that on the left. It doesn't really matter, but I'll put it on the left. Put it on the left. Now, our job is to find the c. Now, you don't really know anything about this except that the left-hand side equals the right-hand side. But we always can pick any, this is true for any value of x. So you want to find a value of x where it's really helpful, right? Basically, everything that you want disappears. So if we were to sub in x equals -1, can you see that x plus 1 becomes 0? So this goes, and this goes. And we're left with a whole bunch of things. So that might not be so nice, actually, because while all this goes, you're going to be left with a whole lot of things. That'll be probably helpful for our question. But the thing is, we actually need to work out what c is before we do that. So what also makes a lot of things go away, though, is if we sub x equals 0. Because if we sub x equals 0, then this entire thing goes away. Because every single term in here has x in it as a product, like something times x to the power of something. So if I sub x equals 0, this entire thing disappears. These things stay, but they're nicer, right? It's just 1, 1, 1. So what I'm basically saying is I'll sub x equals 0. If you sub x equals 0 for the purpose of finding out c, I'm going to end up with nothing left on the left except c. And I'm going to get 1, like, so, I mean, I still have the coefficient at the front, but I can deal with that. So in other words, if I sub x equals 0 in there, I'm just going to get c on the left, because I stress again, every single term in this sigma, this sum has gone, because you're multiplying by 0. This becomes 1, so it's 1 over n plus 3, minus 2 over n plus 2. Plus 1 over n plus 1. And that is our c. Now, it doesn't look like you can really simplify that very easily, so I won't bother, not now anyway, I might do that later. So what that then means is I now have not just a general relationship between the left-hand side and the right-hand side, but the specific C. So my now relationship is the sum from k equals 0 to n of nck 1 over k plus 3, k plus 2, or k plus 3, nck x to the k plus 3. Plus my c, which I'll write out in all its glory here. And that is going to equal the right-hand side, which is this thing here. So we've got 1 over n plus 3, x plus 1 to the power of n plus 3, minus 2 over n plus 2, x plus 1 to the n plus 2, plus 1 over n plus 1, times x plus 1 to the power of n plus 1. And this is now our expression. Doesn't look very nice, but certainly it will work out very nicely very shortly. Because, as I have alluded to, what you're really wanting to do is remember what you're after. You are after a third NC0 plus a quarter NC, not plus actually, that was a mistake on my part, a minus NC4, a quarter, NC1, plus a fifth NC2 minus, and so forth. And if you match that up, and I'll write it out here, all right? So we want to get a third NC0 minus a quarter NC1 plus a fifth NC2 plus plus negative 1 to the power of n plus 3 over n plus 3 NCN. Then you would make that match by subbing x equals -1. And if you sub x equals -1, all of these terms go. You'll end up with 1 over 3 NC0, -1 to the power, and then minus a quarter, so k equals 1, NC1, negative. Yep. So you'll get all of these things. Okay, so if we sub x equals -1 into our expression, then you will get the sum from k equals 0 to n of nck 1 over k plus 3, -1 to the k plus 3. And that will basically really match this up, right? You can see, right? It's -1 to the k plus n plus 3. Like if you sub in n, it'll be -1 to the n plus 3, n plus 3, NCN, right? It basically matches those terms. And then you'll end up with plus 1 over n plus 3 minus 2 over n plus 2 plus 1 over n plus 1 equals 0. That's what we'll have. Which means what we're trying to get, this thing that we're trying to get, the sum from k equals 0 to n of nck 1 over k plus 3, -1 to the k plus 3, which in other words, I mean, taking a look term by term, when you sub k equals 0, it's nc0, 1 over 3, -1 to the power of 3. Okay, so we want that to be, it will be the, so far this will be 1 over, it will be 2 over minus 1 over n plus 3 minus 1 over n plus 1. The expression they want us to get is going to be the negative of that. So the negative of this thing. is going to be the negative of this thing. And this is what we want. This is the expression we want. Or the left-hand side anyway. In other words, we now need to prove that this is the right-hand side that they wanted. So we have 2 over n plus 2 minus 1 over n plus 3 minus 1 over n plus 1. And we want a negative in front. Now you want to show that it's 2n factorial all over n plus 3 factorial. Well, if you were to make this n plus 3 factorial, which is not the usual way you would do this, but if you were to make the denominator n plus 3 factorial, I mean, you can see it's doable, at least on a per fraction basis. It will be n plus 2 times, well, n plus 1 factorial. That, and then times n plus 3. This is going to be n plus 3. You'll need to multiply by n plus 2 factorial. And then your n plus 1 would need to multiply by n plus 3, n plus 2. Your n plus 1 stays. And then you have n factorial afterwards. So what are the new things we had to multiply by? Well, we had to multiply by n plus 3 and a n plus 1 factorial. We had to multiply by n plus 2 factorial. And we had to multiply by an n factorial, a n plus 2 and an n plus 3. Originally, that was a 1, that was a 1, and that was a 2. So now we've got the n plus 3 factorial at the denominator. And now we just have a lot of algebra that hopefully will reduce down to 2n factorial. So putting the negative in, you've got n plus 2 factorial minus n factorial, n plus 2, n plus 3. Sorry. So negative of that is plus, negative of that is plus, negative of this is negative. Our job is to try to show that this is 2n factorial. So let's have an n factorial out where we can. So that's going to be n plus 1, n plus 2, plus n factorial, n plus 2, n plus 3, minus n factorial, n plus 1, times n plus 3, times 2. So we can take out an n factorial. And that leaves us with n plus 1, n plus 2, plus n plus 2, n plus 3, minus 2 times n plus 1, n plus 3. And so we want to now show that this is 2. Can we show that? Hopefully that's not 2. So we've got 2, 3, 1, 2, 2, 3, 1, 3. Okay. So we have n plus 1, n plus 2, plus n plus 2, n plus 3, minus 2, n plus 1, n plus 3. And we want to show this is 2. If we show that's equal to 2, right, you've got that will become 2 and that will become that. So n plus 1, n plus 2, 2, 3, minus 2, 1, 3. Good. So expansion time. Okay, so we've got n squared plus 3n plus 2. The next one is n squared plus 5n plus 6. The next one expanded individually is n squared plus 4n plus 3, but you are subtracting 2 times that. In other words, and you can hopefully see this now, it's 2n squared plus 8n plus 8 minus 2n squared minus 8n minus 6, which is indeed 2. So as we have shown that this entire expression is equal to 2, we have therefore shown that this is 2, and so that is equal to 2n factorial all over n plus 3 factorial. Right. So just recapping the question, which has involved quite a few steps. Just recapping the question, you've taken the identity given, you used binomial expansion, you've compared against what you wanted and recognized that this expression is not sufficient. You've got the fractions, so you'll need to integrate. Integrating was a bit more involved than usual. You had to use integration by substitution on this side. But once you've integrated, and this side was fairly straightforward, once you've integrated, you always need to determine your C. The way to determine your C is to sub in an X value. The common ones to try are 0, 1, and minus 1. All of them will theoretically work, but pick one that is nice and easy for you and fast. So we picked x equals 0 to make all of this go away, giving us C very quickly in relative terms. And that lets us determine our C and therefore our expression over here in black. Once we've got our expression, we can then actually start working on proving what they wanted. We would recognize that this expression we worked for, including x, we sub in our value. In other words, it's a type 1. Okay, it's a type 1. And because it's type 1, we sub in our value of x equals -1, which basically gets us what we wanted to prove, almost. We're out by a negative sign, but it's basically there. So that means this plus this gives you 0. You rearrange and make sure that this expression exactly matches with a negative sign, giving you this expression that you need to evaluate, which you're trying to show is what the questions ask you to prove, which is this thing. It's quite a bit of an algebraic mess, but this is equal to, well, go for what they want. They wanted n plus 3 factorial in the denominator, so we did that, as messy as it is. Take out what the bits you want. Recognize you've got an n factorial. So again, a bit of an algebraic mess, but take that out. What you're left with has to equal what's left, which is the 2. And we do that, and we get it, and therefore, that's how you do the question.